In the first example, we'll look at a warehouse that has conveyor belts throughout. This example is of a 6-zone warehouse with a conveyor system that diverts totes or cartons to each of the zones and then sorts to various packing stations as seen on the left. One major drawback is that conveyor systems often cause barriers to free movement of people and equipment. They dictate the need for zones as well. In order to move around, people have to walk around the conveyor or through gates to get from zone to zone. In our revamped warehouse, we've eliminated the conveyor system altogether. As a result, we have additional cube and storage space to leverage, as seen with the dark blue bays at the bottom of each zone, which is now virtual. This also frees up the pathing possibilities from zone to zone. With this added flexibility, optimization of batches can be improved and is a great use case for DWO. As seen on the key at the bottom left, you'll see the humans in gray picking with the carts in green. Instead of the conveyor belt, the robots in red have taken their place. You'll see the robots carrying the green carts away to packing, as well as empty carts to the staging areas for pickers to begin picking. Robots are used to handle the long travel between zones, packing areas, sorters, and etc. They are not going down the aisles. The robots pick up carts and transfer them. Humans push the wheeled carts down the aisle to each location for picking as dictated by DWO. You'll notice that some of them have cut across their traditional zone boundaries as well. In summary, Lucas DWO batched the orders on the cart to reduce the travel within the picking areas for workers and leverage robots for the takeaway, which is heavy on travel.
In our final example, we're going to apply digital automation to optimize and coordinate the work of humans and robots, orchestration, if you will. This coordination will be handled by our DWO, or Dynamic Work Optimization module. Currently, the robots or AMR company's solution is to have human workers read a robot screen to know where their next action is. But in our example, the pickers will receive their instruction through headset and use voice or scanning or screens to actually confirm the picks. So we're kind of decoupling having to read the screen on the robot from being able to direct and move the pickers or the human labor around. Adding coordination and communication between robots and people will provide significant value in reducing travel and will also result in better positioning of the resources, both robots and humans. Before I start, I will again mention additional advantages of dynamic work optimization, which is the real-time batching of orders. That feature is not represented in this simulation, but could be added to the overall solution. So here a picker is directed to pick location and robot A. Once the first pick is completed, the system takes into consideration the location of the picker as well as the location of all the picks and the corresponding robots. The system directs the picker to the location directly behind them and coordinates moving the correct robot to that location, and also positions robots for future picks. Once that pick is completed, the system directs the picker and the robot to the next pick location. As you see here, the picker is directed to the pick in the next aisle instead of the robot that they could see in the current aisle, which is the current solution envisioned by the current generation of robotics. If the system detects sufficient demand, or if labor becomes available, a new worker, the little dot at the top of the screen, may be directed into the zone. As picker 1 is completing the pick to robot C, to provide a more efficient pick path and distribute work among available pickers, the system has determined that Robot B should be repositioned. And the second picker gets directed to Robot C. Picker 1 and 2 continue to get instructions and complete their picks. Because they're directed, they don't have to scan into each robot before they pick, which is, again, the current practice. They can confirm placing the items to the correct robot or tote by speaking a check string or scanning or using RFID. And we now watch them complete their picks. As Picker 1 completes the pick to Robot B, they can be directed to another area of the warehouse, again based on the demand, because now there's not enough pick density to support 2 pickers in this area. In summary, this slide shows the travel path traveled by Picker 1 with only robot-assisted picking. The total travel distance here is represented by about 412 feet. This slide shows the path with human-robot coordinated picking, showing travel of a total of 202 feet with an over 50% reduction in human travel. And this slide shows the 2 pick paths, kind of the before and after overlaid.